So let's take this cathode ray tube, the CRT, and break it down to the electron gun. Start with the electron gun and a voltage plate that aims the electrons. Start with the electron gun. Let's just take the filament out of the picture just to make it less messy and just say we've created electrons in a space by just sending a current through a filament and boiling off. You literally just boil off some electrons. So then we have a cathode and an anode, which means that we've put a voltage difference across these two plates. Now, because electrons are negatively charged, that means that in order for the electrons to be pushed to the right in this case, this plate, the cathode must be negative and the anode must be positive. Hopefully I got the cathode and anode the right way around. Okay, and what that does is accelerates the electrons, and you put a hole in the anode, and the electrons therefore come out with an initial velocity v sub x. What is that initial velocity? Well, if the electrons are created near the cathode, and they're accelerated through a voltage delta v, then we can simply say that the amount of energy that the electrons get is Q delta V. Remember, that's the amount of energy that you get when you move through a potential difference, Q delta V. And the amount of energy that it gets turns into kinetic energy, so that's 1/2 mv sub x squared. And so we can find the velocity of these electrons. Again, this assumes that they essentially start from rest. So it would really be Q delta V equals 1/2 mv x squared minus 1/2 mv initial squared, where v initial is the velocity they have at the left. We're assuming that's 0, so that's how we get the equation above. It's just energy conservation equation. And so v sub x is equal to, and again, just remember that Q delta V is the amount of energy that you get when you accelerate a charged particle Q through a potential difference delta V. And that that's an energy in either electron volts if Q is the number of electrons, or it's an energy in joules if Q is coulombs, right? If Q is coulombs and delta V is volts, then coulombs times a volt is a joule. Whoops, hold on. Or if it's the number of electrons, right? If it's the n, the number of electrons, E, let's just say E, right? 1E is the charge of 1 electron, 2E is the charge of 2 electrons, times volts, then the energy is in electron volts. Right? That's the electron volt. And we know that the unit conversion between electron volts and joules is because there's 1.6 times 10 to the minus 19th coulombs in an electron times 1 volt equals 1.6 times 10 to the minus 19 volts per EV, volts per electron volt. Sorry, said that wrong. Joules. That's coulombs times volts is a joule. 1.6 times 10 to the minus 19 joules per electron volt. That's our unit conversion between joules and electron volts. Okay, coming back to where we are with the electron gun. That's the electron gun. That's how we give the charges speed and we shoot them at a hole. Then we shoot them through the CRT apparatus and we send them through, again, charged plates with plates with a potential difference. Let's say we send them through plates that have this orientation, right? We can send them through plates that have a perpendicular orientation to direct the electron charges into or out of the page. But if we have the orientation top to bottom, what this allows us to do is to direct the electrons up or down, right? So as the electron comes through and ignoring gravity, we are ignoring gravity because this happens so fast, gravity doesn't play much of a part. We can direct the electrons up or we can direct the electrons down while they're between the plates because we can exert forces on the electrons by putting a potential difference across these plates, right, delta V, and we can vary that potential difference to move the electrons up and down, and then we can do the same thing with plates in this orientation, in order to move the electrons in and out of the page. And so we can hit anywhere on that screen, which is to the right, on that far screen over here. So we can hit anywhere on that screen as long as we can direct them in and out and up and down. So let me first, before we get to the rest of the workings of the CRT and the discovery of the electron, talk about a velocity selector. We actually talked about velocity selectors in Physics 116, so this is all just review. Everything we're doing here is review of 116 material. A velocity selector is the way that you can use to measure the velocity of a charged particle. You're actually selecting out, in a sense, particles with a certain velocity, but it's a way we measure the velocity of a charged particle. And you can argue here that the electron gun, while we can do this analysis on the electron gun to figure out what the velocity is, since the electrons may have an initial velocity when they're boiling off of the filament, this is not exact, and we can measure better what the velocity is using a velocity selector. So a velocity selector is simply, I don't know about simply, but is going to the parallel plate capacitor. Two parallel plates where we put a voltage, that's just called a capacitor, right? But going to these parallel plates here, and let's put a magnetic field on as well. And how do we put a magnetic field on? We talked about it previously. All you have to do is inside of the CRT, you have these plates with a voltage, and you can control the voltage with an outside voltage source. And then you can also put electromagnetic coils. Now, the electromagnetic coils do not need to go inside the CRT. They can sit right outside here and create a magnetic field. There's going to be a pair of them, one on either side of these plates. So it's a little hard to see there. So let's say we have a top view of the plates. The electrons are coming through with some velocity, or maybe some variation of velocities. There's going to be some variation of velocities too. But anyway, the electrons are coming through this first set of plates, and that's just supposed to be one on top of another. This was supposed to be a top view. We're going to the top view of this. And I'm going to put a coil of wire here. This is now drawn in 3 dimensions, and a coil of wire here, so that those two coils are like wheels on a car, right? So it's like this is the axle going through the car, which would be the capacitor plates. And so this is called a Helmholtz coil, right? Helmholtz coils. They're called Helmholtz coils. And it is very well known and understood, and it was in the late 1800s, that you can create a pretty constant magnetic field by putting 2 Helmholtz coils, as long as the distance between the coils is smaller than or equal to the radius of the coils. So as long as the coils are not too far apart, they're relatively close together compared to their radius, then you create a pretty constant field between the 2 coils. And the value of that field is known. And so we'll just say that they create a magnetic field, a constant magnetic field B between them, understanding the details we just talked about. The one thing I didn't say, which I think was obvious, these coils, they're literally just coils of wire that you put a current through, right? You're putting a current through those coils of wire, and you need to make sure that the coils are oriented so that the magnetic field that passes through, each coil passes through in the same direction, so that those 2 fields add in the center, so that there's a magnetic field either to one side or the other, and that's got a magnetic field with a magnitude of B pointing along the axis of the coils, one way or the other along the axis of the coils. Okay. Let's say that we've got a charged particle. Let's just say it's got a charge Q, and we know the charge of the electron Q is 1e, right? Charge of an electron is actually negative 1e, because e is a positive number, or negative 1.6 times 10 to the minus 19 coulombs. Let's make sure we know that as the charge of an electron. On the previous page, I just used the magnitude of the charge, which is the E itself, 1.6 × 10 minus 19. But electrons are negatively charged. Okay, let's say we have a charged particle Q, and it's traveling at speed v. We've got to differentiate between speeds v and potential differences delta capital V. Keep the speeds to be small v's and potential differences to be capital V's. This just shows that we've got a potential difference across the plates that hopefully doesn't get in the way of the path of the electron. It doesn't. And let's say that delta V, hold on a second, ignore that for a second. And then, so those are the plates. Again, we're looking at side view here. And then this is the coil. The black circle is just meant to be the coil, right? Or the Helmholtz coil, which we're going to put in a current I. And we know, therefore, that can create a magnetic field. So we now have the ability to create a magnetic field, which is either into or out of the page, right? Into or out of, into the page or out of the page. So in versus out. So we can create a magnetic field that's into or out of the page with the Helmholtz coil. And we can create an electric field with the potential difference across the plates that's either up or down. So the electric field, it's either up or down. I should probably draw that a little bit differently because we don't want to indicate that we could do both at the same time. It's or, and then or, right? That we can do into or out of the page magnetic field, electric field, up or down. Okay, let's first of all, and so the electric field is created by the potential across the plates. The magnetic field is created by the coils. Let's first turn off the field. E equals 0 and B equals 0. If we turn off the field, what's going to happen to these electrons if they're traveling in the horizontal direction? We're ignoring gravity. They're moving fast. Gravity doesn't play a big enough part here to take into account. They're going to travel along the dotted line. What happens if now we turn on an electric field? We put a potential difference across the plates and we turn on an electric field. Let's say we turn on an electric field. Let me make it purple. We turn on an electric field upwards. If we turn on an electric field upwards, what that means, it's going to push a positively charged particle in the upward direction. So what that'll do is it'll push a negatively charged particle in the downward direction, and I'll make it purple. And the electron will now have a path where when it gets between the plates, it's going to be deflected parabolically downwards. And when it's no longer between the plates, it'll just travel in a straight line. So this is meant to be a straight line. This is meant to be a parabola. Okay. So it'll be deflected downward with an upward electric field and vice versa. A downward electric field will deflect the electron upward. Okay, now let's turn on a magnetic field. Turn off the electric field and turn on a magnetic field. Okay, so what over here, this was, electron goes straight through. Electron goes straight for no field. Straight. And then this is down here. This was E, electric field pointing upward. B equals 0. Now let's turn off the electric field. Turn off the electric field and turn on the magnetic field. What does a magnetic field do to a charged particle? A magnetic field deflects a charged particle perpendicular to its field. We'll have to write down these equations in a second, but you should remember that the magnetic field deflects it perpendicular to the field. Let's write down the equation. The force, the magnetic force, is equal to QV cross B. That's the magnetic force, the Lorentz force. The Lorentz force. And that magnetic force is V cross B. So if the electron is traveling to the right, and let's say that B is in, for B into the page, if the V is to the right and B is into the page, you take your fingers, you point them in the direction of V, and you rotate them towards B, you rotate them into the page, your thumb points up. That means a charged particle, the force will be up on a positively charged particle. On a positively charged particle. That means the electron will be deflected down. So that means that a field, so I won't draw this in the picture, but a field into the page deflects the electron down. Now, just FYI, it deflects it in a circular path until it no longer is between the plates, and it'll be a straight path again, but it'll still look pretty similar to a parabolic path because it's a pretty short distance. And so turning off the electric field, so this would also be essentially E equals 0 and B into the page, right? That's going to deflect it downward. So what is a velocity selector? Now, okay, well, wait, forget velocity selector. Let me go backwards and remind you that we knew that the electric field deflected a positively charged up, but what's the equation? It's Q times E, right? That you can see that the electric field will therefore deflect, therefore Fe is up if Q is positive on a positive charge or if positive charge. So you can see that from those two Lorentz force equations. This is also Lorentz force. It's the Lorentz force equation. Electric force and magnetic force is Lorentz force. Just drawing over here to the left. The Lorentz force is the sum of the two forces. But if one is 0, then it's just one or the other. Okay, so the magnetic force will deflect a charge. An electric force will deflect the charge. So what a velocity selector is let's create two forces, the magnetic and the electric force, that cancel out and don't deflect the charge at all. What a velocity selector is if, for example, on a charged particle, whether it's a positive or negative charged particle, if I have an electric force that pushes it upwards and a magnetic force that pushes it downwards, so I just flip one of those fields, then they work against each other. And I can make them so that their magnitudes are equal so that they cancel. Now, just before I write that down, notice that also says that if the electric force is downwards and the magnetic force is upwards, they work against each other. And they will cancel either way if their magnitudes are the same, right? They'll cancel if QE equals QVB. V cross B is VB, aside, V cross B is VB sine theta. But in this case, theta is 90 degrees because the V is always perpendicular to B. In this case, like, look at your geometry of the setup. So therefore, V cross B is equal to VB. In magnitude, at least. Okay, so the magnitude of V cross B is VB. Okay, so the two forces, the magnetic force will cancel if QE equals QVB. So therefore, V is equal to, oh, look at that, E over B. The two forces will cancel if the velocity of the charged particle is the magnitude of the electric field divided by the magnitude of the magnetic field. How is this a velocity selector? What does that mean? What this means is let's say that you have electrons traveling through here at some distribution of velocities. Right? So there's some going faster, some going slower. So when you turn on the electric field, they'll all deflect somewhat differently depending on how fast they're going. And the magnetic field, they'll deflect somewhat differently. But if we turn on the electric field and magnetic field and we vary the electric field and magnetic field until we get some electrons that are traveling straight through, we vary them until we get some electrons that travel straight through, then we know the velocity of those electrons traveling straight through is whatever value of E we have divided by whatever value of B. Some others might be going up there, some others might be going down there, but the ones that travel straight through have a velocity of E over B. Done.